A pleasant day to everyone. We are here to present our performance innovative task in differential equations. By the way, we are the Group 6 with the following members: Nathan Josh Mendez, Princess Bea Mercado, Samantha Alizon Nakalaban, Amiruddin Noor, and yours truly, Harvey James Merlo. In this video, we are going to report about the application of Newton's law of cooling in civil engineering. So, let's begin.
We're going to cover a few key topics related to Newton's law of cooling and how it applies in the field of civil engineering.
Let's take a look at the theory behind Newton's law of cooling. As stated in this law, the rate of temperature change of an object is proportional to the difference between the object's temperature and the surrounding ambient temperature. In this equation, T is the temperature of the object at any given time. So T ambient is the constant ambient temperature, while K is the cooling constant, which depends on the material properties and environmental factors. So now let's see how Newton's law of cooling applies to concrete curing. So a vital process in construction, when fresh concrete is poured, it goes through the exothermic hydration reaction. This reaction releases heat, raising the concrete's temperature about around 70 degrees Celsius initially. For the concrete to properly cure and gain the necessary strength, it needs to cool down gradually. If it cools too fast, the concrete can crack and lose its structural integrity. On the other hand, if it retains too much heat, it may not gain the strength it needs. Newton's law of cooling helps us predict how concrete will cool over time, considering the difference between its initial temperature and the surrounding ambient temperature, which is typically around 25 degrees Celsius. So in civil engineering, understanding and controlling the curing process using principles like Newton's law of cooling is essential to achieving optimal concrete strength and durability. It's a great example how fundamental physics plays a critical role in the safety of longevity of our infrastructure.
Starting with the initial temperature of the material. In the Philippines, an ideal initial temperature for concrete after the hydration reaction is generally between 28 to 35 degrees Celsius. This range is considered optimal for achieving a good balance between strength gain and minimizing the risk of thermal cracking. So in a problem which shows 32 degrees Celsius, next is the ambient temperature. The ideal ambient temperature for pouring and curing concrete typically ranges from 20 to 32 degrees Celsius. This range is considered optimal because it helps ensure proper hydration of the concrete without excessive evaporation or thermal stress. So in our problem, we chose 29 degrees Celsius. Lastly is the cooling constant. The ideal cooling constant K for concrete in the Philippines can vary based on environmental conditions, but a typical value often used in engineering practice ranges from 0.02 to 0.05 per hour. This range accounts for the specific tropical climate, including factors like humidity, wind speed, and the characteristics of the concrete mix. It may be beneficial to conduct field measurements or consult with local engineering guidelines for more precise values tailored to specific project conditions.
Now, we will be finding the particular solution of the given equation. The first step is to separate the variables temperature and time. Next, we integrate both sides, which results in ln temperature minus 29 equals negative 0.02 times time plus c, where c is the constant of integration. Then, to eliminate the natural logarithm, we have to exponentiate both sides, which simplifies to t minus 29 equals e raised to negative 0.02 times e raised to c. Since e raised to c is just another constant, let's define it as c1. So we have a general solution of t equals 29 plus c1 e raised to negative 0.02 times time. Since we are given that at time is 0 and the temperature at 32 degrees Celsius, we use this condition. We then input the values and it becomes 32 equals 29 plus c1 times e raised to negative 0.02 times 0. Since e raised to negative 0.02 times 0 is equal to 1, we multiply this to c1, making it c1 equals 32 minus 29, which is equivalent to 3 degrees Celsius. When finding the particular solution of the equation, we have to substitute C1, which is 3 degrees Celsius, into the general solution. Then, the particular solution to the equation is temperature equals 29 plus 3 times e raised to negative 0.02 times time. This function describes how the temperature of the concrete changes over time as it goes towards the ambient temperature at 29 degrees Celsius.
Proper temperature control during curing is crucial for ensuring the material strength and durability. Both rapid and slow cooling can negatively impact the final structure. Fast cooling. If concrete cools too quickly, the surface contracts faster than the inside. Slow cooling. If cooling occurs too slowly, the concrete might not harden properly. Uneven cooling. When the outer layers cool faster than the inside, the concrete strength becomes uneven. To avoid these problems, builders need to control the cooling rate. They might use covers or water mist to ensure steady cooling, allowing the concrete to gain strength uniformly and avoid cracks.
Down to our last slide, I will discuss some additional factors that could influence the cooling rate and then try to incorporate it in our model. First is the different types of cement. Different types of cement affect how much heat is produced during the curing process. Example, the rapid hardening Portland cement, which generates heat quickly, and ordinary Portland cement that generates heat more slowly. Since RHPC produces more heat, we would use a larger K value for it. We can adjust K based on the type of cement we're using. Now when mixing concrete, the temperature of the water added can influence the initial temperature of the concrete. For example, if you use cold water, it can lower the starting temperature of the concrete mix. This can lead to quicker heat loss, may affect the curing process, and understanding the curing process and managing the temperature is key to building long-lasting structures. Thank you so much for listening. That's all for our report.